Good. So today I'll be presenting to you a parallel resonating plate setup for characterization of viscous and viscoelastic fluids. Here's an outlook of my presentation, and I'll move on to starting by a small introduction to what single resonating plates are. Single resonating plate for viscosity and density measurement. There's an example of. How does this work? The pointer. Okay. There's an example of a single resonating plate for viscosity density measurement, and here we see the dependence of such a plate for the square root of viscosity density. These plates are sensitive for low range, but we see a very big reduction of the sensitivity of high viscosities. The solution for that, as we came up with, was to use two plates instead of one, and end up with such an arrangement. The way our sensor works is that we actuate the bottom plate by the use of, so we electromagnetically actuate the bottom plate by Lorentz forces, with I1 and I2 being our actuation ports where we apply an alternative current. And O1 and O2 would be the readout ports where we read the motion-induced voltage. We use for the actuation two neodymium magnets. And as for the actuation of the upper plate, so it happens when the lower plate is actuated, it generates plane shear waves in the fluid. The higher our viscosity, the larger our wavelength and penetration depth. And the more increased the coupling with the upper plate is. And as I said, we read out our motion-induced voltage. Good. This is a typical assembly of one of the sensors, where so we manufacture the plates themselves by lithography and wet etching of 100 micrometer thick nickel brass or new silver metal sheets. We use two spacers of 100 micrometer, so two Teflon spacers of 100 micrometer to separate the plates. And we clamped both plates between, so F2, FR4 plates. I should also mention that the dimension of the plate here is 8 millimeter in diameter with a hole of 3 millimeter. One more note on the hole you see, so the hole here is used for filling of the fluid samples. Okay, what is the benefit of using parallel plates? First of all, it allows us for the analysis of complex fluids, because most fluids are, so a lot of fluids of interest are viscoelastic in nature and have very high viscosities, at least in comparison to, so by very high I mean above 1 Pascal second. It allows the use of very low volumes. In our case here, we're using 8 microliter, but we can also, so the volume depends on the separation of the plates. And the benefit, the major benefit, is that we have very high sensitivity at low viscosities by measuring the frequency response on the actuation side, and we can increase the range of high values by measuring the shear wave transmission on the upper plate. Good. So our plates were modeled as lumped mechanical oscillators with the following equations of motion written in the frequency domain. It looks like this, where D is the damping, K the stiffness, and M the mass of the resonator. This yields the following equations for a coupled system, where V1 is the equation for the bottom plate and V2 for the upper plate. F1 is the Lorentz force, the applied Lorentz force, and FL is the fluid force, which in a finite gap looks like this. K, so the velocity has the following shape, and K is the wave number, and is a function of rho over G, G being the complex viscoelastic modulus, which for Newtonian fluids is equal to J omega eta. Eta is our dynamic viscosity, rho the mass density, and A the area of the resonator coupled, so the coupled area of the resonator where the fluid is. Good. From previous work, we know that the equivalent circuit for one of the plates we have is the following, with the following values for LR, CR, and R, which are functions of K, M, and D respectively. B being our magnetic field intensity. And the coupling of the fluid we modeled as a transmission line with an impedance Z0 and the propagation constant gamma. The transmission line also has the parameters, the length, which is the separation of our plates, the complex viscoelastic modulus, naturally, and the mass density, which are all included in the formulas. And our equivalent circuit model looks something like this. Good. For the sensor characterization for now, we stuck to measurements in fluids in order to determine the dependence of the sensor on changes in viscosity and the temperature dependence of the sensor, both when it's loaded with fluid and when it's operating in air. The fluids we used were viscosity standards and a mixture of silicone oils that should be around 3 Pascal second at 25 degrees C. A value to note here is also the kinematic viscosity, which is eta divided by rho. Good. For the data analysis, we had to extract the resonance frequency and the quality factor, which we did by fitting a standard second-order frequency response to our signal. And here is the frequency response of the plates, so the bottom and the upper plate, operating in air when they are unloaded, and the temperature dependence of the resonance frequency and the quality factor. The temperature dependence is the same for both plates, so I only showed one of them. When measured in liquid, the higher the viscosity of the liquid, we noticed an increase of the intensity of our signal and of the amplitude and the frequency shift upward. Okay, these are the results of the resonance frequency dependence on eta, the viscosity, and the kinematic viscosity, eta over rho. And here's our quality factor dependence on those values. The quality factor shows a very clear dependence on it, but there is no simple dependence of Fr on the viscosity. Okay, the sensor, when the field sensor has the following temperature dependence, and so we still need to isolate which effects are those of the resonators and which are those of the fluids, but clearly some of them are for the fluid, and if such, that means that we have reached values of 17.1 Pascal second, which is quite high for such resonators. Good. As conclusion, we have introduced parallel resonating plate setup for fluid property sensing with high sensitivity for low viscosity and an increased range at high values. We have introduced the equivalent circuit model and showed the dependence of the sensor on changes in viscosity and density. Future steps will include validating the model to the measured data, measurement with various fluids and plate separations to also determine the plate separation, the behavior of the sensor, and to develop a more suited measurement setup specifically for these resonators, especially one where we can have an ease of a filling of the setup. Thank you.
So now we have time for a couple of more questions. Please.
One of the things you probably have to validate is what you're seeing is a really a shear wave or your compressional wave, or have you be able to know, how can you tell that's the shear wave instead of a compressional?
Well, because of the way we're actuating it. So we are actuating in an in-plane shear mode. The wave will be more complex, but we're mainly actuating a shear mode. So working with the assumption that we're actuating a shear wave. Yeah.
A compressional mode would also...
Yeah, so the wave would look more complex. So it might have other components.
Yeah.
Yeah.
More questions? I would like to ask you to comment on the figure which you had later on, that there was this frequency shift and the amplitude increase. That I think, yeah.
Yes.
Figure.
Okay, well, what's the question exactly?
So that you observe the frequency shift and the amplitude
Well, the frequency shift itself is still under investigation, let's say, but the increase of the amplitude is basically because of the increase of the coupling. So the higher our, the higher the viscosity we have, the higher the coupling of the shear wave to the upper plate is. So
And what could be the frequency shift?
in this case, it could also depend on the viscosity change. I really don't know at this point.
Any other comments, questions? Not, thank you very much.
But